All right, so this week, folks, we're going to be talking about entanglement, which is kind of at the heart of all of these quantum information systems that we've been introducing. So the main reading is going to be from Sutter, chapter 8 and 9. There are a lot of typos in this part of the book for whatever reason. So just look alive, pay attention. I'll try to point them out when I find them in the lecture. So 2022 Nobel Prize in Physics was awarded for entanglement. It was really good timing for the first time I taught the class. So that's a great piece of reading. There's also a really good section in the IBM quantum learning curriculum in sort of the KISE landscape on entanglement in action. There's also a couple literature papers on a one-way quantum computer. All right, so last week we were talking about coherence, and we saw a few cool examples of understanding elements of quantum mechanics and coherence by thinking about experiments with light. And one of the kind of variations of the double slit experiment that I wanted to talk about was called the quantum eraser. And it actually fits in perfectly to kick us off this week to talk about entanglement. Because an essential component of the quantum eraser experiment is a crystal that entangles the photons. So that kind of gives us a physical place to begin talking about entanglement. So the process by which photons become entangled in the quantum eraser experiment that we'll talk about in a second is through a nonlinear optical crystal, and once the light goes into this nonlinear optical crystal, it undergoes a process called spontaneous parametric downconversion. So this process converts one photon into two photons of lower energy. And the process needs to conserve energy. So you have sort of half the energy of the light that you put in coming out in the form of two photons. And you also have to conserve momentum. And this is a really important part of understanding the experiment. So you put in your pump light, and you get out two photons that have been downconverted. We call one the signal photon and one the idler photon. And like I said, this happens in typically a nonlinear optical crystal. In this crystal, phase matching is most commonly achieved using a birefringent nonlinear optical material whose index of refraction changes with polarization. And the conversion, this process of spontaneous parametric downconversion, is very, very, very inefficient. So this process happens for it happens for about 4 pairs of photons per 10 to the 6th incoming photons. So it's very inefficient, very low probability, even in the best materials. All right, so when we think about this process happening, you want to have the picture on the right in your head. So we have our crystal. A really common example of the type of material that is used is called beta barium borate. So that's a classic nonlinear optical material. Lithium niobate is another one. And so most of the photons from your laser continue straight on through the crystal, and so that's shown in the red line. But occasionally, some of the photons undergo this spontaneous parametric downconversion process. And the result of that is that correlated photon pairs have trajectories that are constrained along the sides of two cones whose axes are symmetrically arranged relative to the pump laser. So you can see in this example, they're kind of vertically disposed relative to one another. And like I said, the two photons are always symmetrically located on the sides of the cones because of that need to conserve momentum. Okay, so we have these two cones that are generated, and the momenta in different pairs of photons along the edges of those cones are complementary to one another. And there's two special locations on these cones, and they're shown in these neon green lines. And these are the lines where the two cones intersect. So where the two cones intersect, we have entanglement of the polarizations of the pairs of photons emerging just at those points in our light cones. So these two photons that come out have an equal weight quantum superposition of the unentangled states. So we have, if our unentangled states are horizontal polarized and vertical polarized, then we have HV and VH, corresponding to the left-hand side photon and the right-hand side photon. So this is like a real practical example of how entanglement arises. Okay, so we have this process that generates these two photons that are related in terms of momentum, and at certain places in these cones that are generated, we have this intersection of the horizontal and vertical polarizations, and because they intersect, those two photons are entangled and related to one another. Okay? So how does this operate in our quantum eraser experiment? So a quantum eraser experiment is an interferometry experiment, and it's, like I said earlier, a variation of the classic double slit experiment. And what it shows us is that when action is taken to determine which of the two slits the photon passes through, the photon can no longer interfere with itself. And so when a stream of photons is marked in that way, then the interference fringes that are characteristic of the double slit experiment won't be seen. So how this experiment works is you have, typically in this example, you have an argon laser emitting 351 nanometer light. You focus that light through your beta barium borate crystal. So here's where entanglement happens, as we just described. And we generate these two entangled pairs of photons in very low probability. But for those two, we sort of know what those two trajectories are in this material. And so we have two photons that are entangled coming out at different paths. So the first photon, so we'll call this path 1, it directly goes to a polarization resolving detector, while, so this is our DP. And the second pair in our entangled pair, second photon in our entangled pair, goes through a double slit mask to a second polarization resolving detector. So we can see here's our double slit, here's path 2. And so both detectors are connected to a coincidence circuit so that we can ensure that only entangled photon pairs are being counted. And we have a sort of stepper motor that's scanning across the target area, producing our interference map. So this will give us the traditional interference pattern in the double slit experiment. So the next thing that's done in the experiment is I put a circular polarizer in front of each slit of the double slit mask. So here's my circular polarizers. I have a right circular polarizer and a left circular polarizer marking each of the slits. So which slit corresponds to which polarization depends on how you set up the experiment, but you know which is which. The polarization is going to be measured at the second detector, and that's what marks the photons, and that destroys the interference pattern. So the last part of the experiment is I place a linear polarizer, so that wasn't there before, now I'm putting it in the path of the first photon of the entangled pair. And this is going to generate diagonal polarization. in my first photon. And because these photons are entangled, entanglement ensures that we have a complementary diagonal polarization in the entangled partner that goes through path 2. So that's passing through the double slit mask, and this alters the effect of the circular polarizers. So each will produce a mix of clockwise and counterclockwise polarized light, and so the second detector can no longer determine which path was taken, and so the interference fringes come back. So it's a pretty cool experiment. And you can set this up at home using like little polarizers and like a razor as your double or quadruple split, depending on how many razors you have lined up. So it's a really fun thing to try. So this YouTube video kind of walks you through how to do it. And there's a nice Scientific American article that'll walk you through how to do it, maybe a little more sophisticated than the YouTube video. But it's cool to see that you can just kind of, yeah, it's a very simple setup, can be set up more fancily in the lab. But the reason that this is kind of interesting from a quantum mechanics perspective is that it basically offers us an alternative perspective on interference and the loss of quantum coherence in terms of indistinguishability of paths. Alternate paths are made distinguishable in this experiment by correlating them to the environment, to these, going through these filters. And so depending on how we reduce the resulting enlarged Hilbert space in our system, we can choose to retain the which way am I going information and have no interference, or we can reestablish indistinguishability of paths and interference by introducing that diagonal polarization filter. And what's really interesting about that is you can actually make that choice long after the original interfering system has been detected by correlating the data with the results of your measurement on the environment with which the system was entangled. So kind of cool. So you can kind of delay your marking and get the same results. So one of the things that the quantum eraser experiment teaches us is that the state involved in interference is the total physical state, which includes the photon spatial wave function, it includes the photon polarization, and it even includes distant atoms or parts of the system with which the photons have interacted. And so the magic of the quantum eraser comes about through entangling the interfering system with some other degrees of freedom from the environment. So it's a pretty neat example. Questions about BBO, photon entanglement in nonlinear materials, or the quantum eraser? All right. Okay, so we talked a little bit about tensor products a few weeks ago, and we need to bring them back today because we're going to be talking about entanglement, and entanglement requires us to think about tensor products. So remember, tensor products interleave two vector spaces. We basically make a new vector out of two old ones. And tensor products are a particular way to build a new vector from an old vector, or a new vector space from an old vector space, because there's lots of ways that you could, in principle, do that. So if we take two vectors, we'll call them V and W. We'll call V this column vector 1, 2, 3, and we'll call W this row vector, or another column vector 4, 5. We can build a new vector called the tensor product, and we just label it as V X with a circle, tensor product W. But we want to understand what that vector is really like. And we can also ask, beyond these two vectors, if we had two vector spaces, we can call them, bold V capital and bold W capital. can we build a new vector space that's also a tensor product of those two? Okay, so we have these two vectors, v and w, that I just drawn. And let's try to make a third vector out of v and w. But the question is, how do we do this? So we can have two ideas. So option one is I can stack them. So I can take v and w, and I can make the following vector, 1, 2, 3, 4, 5. The option two is I can multiply the two components together. So this, I can multiply the two components together to get the column vector 4, 5, 8, 10, 12, 15. There we go. So the first option gives a new list of n plus m numbers, while the second option gives us a new list of nm numbers. The first gives us a way to build a new space in which the dimensions add, and the second gives us a way to build a new space where the dimensions multiply. This first option is called the direct sum. This is the same as the direct product. And the second is our tensor product. And so that's sort of it. So you can see kind of graphically on the left, option one is our direct sum, where we're just kind of adding all the numbers and making a bigger vector out of two smaller ones. And on the right, we're interleaving the two vectors to get this kind of product vector. So you can think about tensor products as kind of like a grown-up version of multiplication. It's what happens when you systematically multiply a bunch of numbers together and then organize the results into a list. It's like multi-multiplication. Typically, a vector in our tensor product space is actually a weighted sum of our basis vectors. So we have to ask ourselves, once we generate the tensor product space, what are those basis vectors? We know there must be n times m of them, since the dimension of our v vector space and our w vector space were nm. And we'd expect them to be built from the basis of v and the basis of w. And so we have to think about constructing new things from old things with the consideration that the bases matter. So if I think about v1 being 1, 0, 0, and v2 being 0, 1, 0, and v3 being 0, 0, 1, and I think about w1 being 1, 0, and w2 being 0, 1, then if I wanted to do v1, tensor product of v1 with w1, that would just give me 1, 0, 0, 0, 0, 5, and et cetera. You can write out the rest. So if we think about the vector spaces, it's the vector space whose vectors are linear combinations of the little vi, vj, wj, sorry. So for example, if we had a couple vectors in this space written as 7 v1 tensor product with w1 plus 3 v3 tensor product with w2, then that would give me 7, 0, 0, 0, 3. Come back. So our V, tensor product of V and W is also technically called the outer product. And we've seen those before. If we're thinking about complex vectors or complex vector spaces, then this outer product is also, we recall, equal to V times the adjoint of W. And we remember that when we did this before, when we looked at this outer product, we would write down if V was 1, 2, 3, and W was 4, 5, we would do the column vector times the row vector here, because it's V times the transpose of W. And that would give us this matrix here, 4, 5, 8, 10, 12, 15. And that seems to conflict with what I just said on the last slide. So I just said on the last slide that I wanted to write my tensor product as this column vector, 4, 5, 8, 10, 12, 15. And I wrote it a different way here, because I was thinking about it as an outer product. But these two go hand in hand. Any M by N matrix can be reshaped into an M and M by 1 column vector and vice versa. So they are the same thing. And this is sometimes referred to as matrix vector duality. And if you've ever heard of process state duality, it's very much the same thing. So we can think about a matrix, the tensor product of V and W, as a process. It's a concrete representation of a linear transformation. And on the other hand, we can think about our tensor product of V and W as a vector. And a vector is a mathematical gadget that we and physicists use to describe the state of a quantum system. So matrices encode processes, and vectors encode states. And the upshot, I guess, is that a vector in a tensor product can be viewed in either way simply by reshaping the numbers as a list or as a rectangle. Yeah. So when we're thinking about this from the perspective of our qubit systems, a vector is the mathematical gadget that we're using to describe the state of our quantum system. If we have our qubit, then perhaps we want to know what it's doing or what it's capable of doing, or the probability that it'll be doing something in the future. So we're asking, what's its status? What's its state? And to answer this question, we need to think about our qubit being represented by a unit vector in a vector space. And in our particular system, we're thinking about vectors of length 1 in the two-dimensional complex plane. If we have two of our quantum particles, and the state of that two-particle system can be described by a density matrix on the tensor product of their respective state spaces. So we know that a density matrix is a generalization of our unit vector. It accounts for interactions between the two particles. It allows us to deal with mixed systems. Like I just said, instead, we don't have to consider sort of all the collective states in a single instance of C2. We're going to use the tensor product of the two copies and the tensor product of the quantum state vectors. So the result of thinking through this is that we're going to get a four-dimensional complex vector space in our entanglement of two qubits, as an example, where the 4 is 2 times 2 rather than 2 plus 2. And the tensor product is the machinery that's going to allow us to build these quantum systems from 2 or more other systems. And the notation for working with these tensor products starts out as kind of bulky, but the Brockett notation comes in to rescue us, and we'll get it simplified. All right. So here we go. Let Q1 and Q2 be our 2 qubits in the standard orthonormal basis kets for our state spaces as normal. So we have psi 1 is A101 plus B111 with our probability amplitudes normalized, and psi 2 described in just the same way with different probability amplitudes A2 and B2. So that gives us the 4 kets shown here. So we have the tensor product of 0, 1 with 0, 2, the tensor product of 0, 1 with 1, 2, the tensor product of 1, 1 with 0, 2, and the tensor product of 1, 1 with 1, 2. And those are our basis for our combined state space for our 2 qubits. And so from the standard properties of tensor products, we can write down the tensor product of these 2 qubits as A1, A2, tensor product of 0, 1, 0, 2, plus A1, B2, tensor product of 0, 1, 1, 2, et cetera, et cetera, et cetera. So this seems kind of bulky, and that's why we're going to use the kind of Brockett notation to help us simplify things. So the first simplification we're going to use is we're going to assume, or we can assume, that there's a tensor product between our basis kets coming from the original but different qubit state spaces. So we're going to just omit the little tensor product symbols on the right-hand side of the expression we just wrote. So that simplifies to what we have here. The tensor product of our 2 qubits is just as written, where the tensor product symbols have been eliminated. So the second simplification is that we don't multiply kets in the same state space, and so we can just drop the little subscripts 1 and 2 on the basis kets. So we just are going to use the order in which they appear as our knowledge of which one they came from. So this one's 1, this one's 2, this one's 1, this one's 2, 1, 2, 1, 2. So that's the second simplification. And then the third simplification is that we can merge the adjacent basis kets inside of a single ket. And the new notation that we get kind of reflects what Dirac kind of wanted us to love about his notation. So the tensor product of our 2 qubit states is just going to be A1, A2, 0, 0, A1, B2, 0, 1, B1, A2, 1, 0, B1, B2, 1, 1. All right, so if we use general coordinates, it might look like this. And since we're going to be looking at and applying matrices, we can remember that we can write out these 2 qubit states as column vectors. So 0, 0 is the column vector 1, 0, 0, 0. 0, 1 is the column vector 0, 1, 0, 0, etc. So we can compute those column vectors from our original single qubit bases. And I guess it would be useful to look at the math to do that. So just take a second and think about how to compute this standard 4 entry column vector from the standard 2 entry column vectors for our starting qubits. All right, so that's what we're doing. We're going to do the tensor product of 0 with 1. We can write them in their column vector notation. And so that gets us to the following expression. So we have 1 times 0, 1, 0 times 0, 1, which is just what we wrote. Right. So one thing that we should remember is that the inner product of 0, 1 with itself is 1, but the inner product of 0, 1 and 1, 1 is 0. And this is generally true. When both sides are equal for these 4 vectors, then their inner product is going to be 1, and when they are unequal, their inner product is going to be 0. And this is a restatement of saying that they're an orthonormal basis. All right. So what about the coefficients? We can look at the coefficients in our expression here. So we have A1, A2, A1, B2, B1, A2, and B1, B2. We can ask ourselves, is it still true that the sum of the squares of the absolute values of the coefficients still equals 1? And if yes, why would we expect that to be the case? Anybody have a thought? They better be, right? It better work. So the sum of the probabilities of each case occurring has to add up to 1. And by extension from the 1 qubit case, we would expect that the coefficients here of this entangled state would be corresponding to probability amplitudes. And the probability of getting 0, 1, for example, would be A1, B2 squared. And so if we did the sort of sum of the squares as before, we would have A1, A2 squared plus A1, B2 squared plus B1, A2 squared plus B1, B2 squared. And we would hope that that would equal 1. And of course it does. So you can just rewrite this as pull out the A1s, for example, and pull out the B1s, for example. So if we did A1 squared times A2 squared plus B2 squared plus B1 squared times A2 squared plus B2 squared. That's 1. That's 1. Yes. So that's just A1 squared plus B1 squared, and that's just 1. So that's good. Entanglement, we can still think about these coefficients as probability amplitudes, and the sum of the squares still needs to equal 1. All right, so measurement is going to cause the state of each of our qubits to collapse to 0 or 1, just like before. And the question is, do they operate independently, or can there be combined qubit states that express some linkage between the two? So we have, at any given time, 2 qubits in superposition states represented by our linear combination of vectors, 0, 0, 0, 1, 1, 0, and 1, 1. Our combined state looks like the sum, where the squares of the probability amplitudes equals 1. And through measurement, our qubit states are forced to collapse irreversibly, and the probabilities are as normal. And we can always convert or read out our qubit states to classical bit strings if that ends up being useful. So let's think about an example. So if our qubits, Q1 and Q2, are in this combined state, then when we measure, what do we expect? We expect if we measure 1, 0, well, let's see. What do we expect when we measure this system? We expect to get 1, 0 half the time. Yeah, half the time. And we expect to get 0, 1 half the time. So given a large number of measurements, that is the outcome we would expect based on the probability amplitudes that are written there. So based on this combined state, we would never see 0, 0 or 1, 1. All right, so now I'm going to give you qubit 1, and I'm going to keep qubit 2. And I'm super excited to have my qubit, and so I'm going to immediately measure it. So I have Q2. And I measure it, and it gives me a 1. What do you get? You say 0. Explain why. Yeah, you got it. All right, so there's 2 possible states that could be measured to get a 1, right? It's 0, 1 or 1, 1. But the probability of getting this is 0. So when measured, you have to get a 0. Before measurement, the qubits were in a state of entanglement. They were so tightly correlated with one another so that when the measurement value of one is known, it uniquely determined the second with no question. You knew right away what it was. So you can't do this with bits. With superposition and entanglement, this is the big key differentiator between our quantum and classical computing. Oh, I wrote it all down. All right, so the entangled state we just used is known as a Bell state. So here they are. This is the one we just looked at, psi plus. And there are 4 distinct Bell states. So there's square root of 2 over 2, 0, 0, plus square root of 2 over 2, 1, 1. There's square root of 2 over 2, 0, 1, plus square root of 2 over 2, 1, 0, etc. Together, these 4 states are an orthonormal basis. For our C2 by C2 tensor space. And they're named after John Stuart Bell, who was a physicist from Northern Ireland. And we can write down, based on the things we've kind of just been thinking about, a general statement for the requirement for entanglement. And here's one of these annoying typos. All right, so let psi be a 2-qubit quantum state in my tensor product space. Psi is entangled if and only if it cannot be written as the tensor products of 2 1-qubit kets. So I have the tensor product of my 2 qubits written as shown here. And I can kind of think through how this works out for one of my Bell states. So let's suppose that the Bell state that we were looking at before is not entangled. So that means there exists some values A1, B1, A2, and B2 with the following expression being true. So this would tell us that A1, A2 equals 0. A1, B2 equals square root of 2 over 2. B1, A2 equals square root of 2 over 2. And B1, B2 equals 0. So from the first expression here, I know that either A1 or A2 is 0, right? So let's assume A1 is 0. That would mean that B1 times A2 is equal to square root of 2 over 2, and that's A1 times A1 times B2 is equal to square root of 2 over 2, and that's not possible. That's a contradiction. So then A2 must be 0. And again, B1 times A2 needs to be square root of 2 over 2, and that can't be if A2 is 0. So that's also an impossibility. So this means we cannot write psi plus as the tensor product of two 1-qubit kets, and it is an entangled state. If a 2-qubit quantum state is not entangled, then we can separate it into the tensor product of two 1-qubit states. And for this reason, if a quantum state is not entangled, then it is separated.